welcome to the 6th International Congress on Information and Communication Technology. And here is a track on communications. My name is Dr. Ezekiel Okike. I'm a senior lecturer at the University of Botswana. I'm also a senior member of the IEE. So we hope to have a very wonderful session. Each presenter has 12 minutes, and then we will have 3 minutes of questions and answers. May I right away call on the first presenter, Communications Management in Security Risk Assessment. Joanne, are you there? All right.
Yes.
Please go
yes.
ahead.
Good afternoon.
Good afternoon.
Good afternoon. I am sorry for not sharing my camera. I'm having problems with connectivity, so I wish you can hear me well and you can see the presentation.
Yeah, so we can hear you clearly.
We can hear you. Go ahead.
Okay, fantastic. Can you see my screen?
Yes.
Yes.
Good. Well, good afternoon, everybody. It is still 9 a.m. here in Peru. My name is Juan Zárate, and I'm speaking on behalf of myself and Dr. Osvaldo Turpo-Rivera, Dr. Maribel Díaz-Zavala, and Master Fernando Paritito from Universidad Nacional de San Agustín in Arequipa, Peru. As you can see, our paper is titled Communications Management in Security Risk Assessment. I'm going to go a bit fast in order to cover all what I have to share with you. We place a special interest in the security of network architecture to avoid data and economic losses, and we also paid special interest in risking the pillars of computer security, which are confidentiality, integrity, and availability. We know that it's possible to reduce risk levels, lowering the impact of threats and attacks without high money investments or having too many staff involved. We started with these questions. How can we be aware and manage the risks the computer system is exposed to in an orderly manner? And how can we consider adequate procedures and plan and implement the corresponding security controls? And we had an a priori answer, by keeping a historical record of the traffic generated, which is made public in the event of an unknown security failure. And this is a way to measure the impact of the failure in the organization. We have these 6 objectives. We consider these 6 objectives for the research: early detection of attacks, identification of vulnerabilities of the organizations in terms of their communication systems, access control to restricted services through security policies, determination of the operational impact of failures in the information and communication systems, linkage with the forms of prevention to the attacks on network infrastructures, and traffic control. And we came to this concept with man in the middle, which allows an attacker to monitor the communication exchange between 2 parties, and which lets the attacker to take the traffic and evaluate through their machine. And we know that most existing systems that discover man in the middle focus on detecting the mechanisms used by attackers to direct traffic to their devices. So this is what I have in our background. And man in the middle is generally carried out by spoofing the access point network and the clients. We have the Salhash algorithm. We have alert correlation systems to mitigate the problem of false positives. And when we have IP simulation, the IP addresses can be easily spoofed, making it difficult to filter legitimate packs from spoof ones. So the system allows the quantitative evaluation of the probability that an alert issued due to an anomaly can become a real threat. And that is the background, and this is what we did. As you can see here, this paper presents a new detection scheme based on the coincidence of the payload of the frames exchanged on the network. The proposed scheme is independent of the mechanism used to launch the man-in-the-middle attack. The experimental results shows that this scheme can achieve a very good detection performance if it is configured properly. We use the information security methodology to support the development of security based on strategies and plans for the protection of the confidentiality, integrity, and availability of information systems data. We implemented the plan, do, verify, and act PDVA model for the development of an information security management system, ISMS. As you can see here, the information security methodology was designed to support the development of security based on strategies and plans for the protection of the confidentiality, integrity, and availability of information systems data. This methodology distinguishes 4 processes.
Yes,
Identification.
Sorry to interrupt, Juan.
Yes.
Actually, you are still on the first slide. Can you make it, slideshow or something?
Sorry?
Yeah, can you try to move forward? You are still on the first slide. Maybe
to the first slide.
Yes.
Yeah.
Actually, you are still on the first slide. So
this one.
So can you do the slideshow or something, because we are able to see only your first slide, not others.
Yeah, maybe his network is very slow and it's taking time to load. So because of his time,
yes.
If it can move, keep on talking. We'll listen to you.
Okay, you cannot see this slide that has a chart.
No.
We're only seeing the first one.
Wow, I'm sorry. Let me check. I'm going to share it again.
Yes, please.
Because it does not let me see that you are there. Okay, let's see.
Yeah, it's okay.
Can you see a slide that says security strategy?
Yes.
Okay, good. So we're talking that this methodology distinguishes 4 processes: identification of methods, tools, and techniques of fraud attacks, establishment of proactive and reactive strategies aimed at minimizing security policies, tests to implement proactive and reactive strategies in order to improve the security policies and controls to be implemented, and training of incident response teams. When we start, we also use the plan, do, verify, and act PDVA model to implement an information security management system. And we have the planning, which started by the definition of security policies, objectives, processes, and procedures for risk management and information security improvement in order to deliver results consistent with the policies and overall objectives of the organization. We have the implementation, which main objective is to guarantee the appropriate execution of the selected controls and their correct application. We have the verification, which evaluates and verifies the performance of processes against the safety policy and its objectives. And also, it masters in the control of security of processes and reporting results to the management for review. And the intervention for which development of corrective and preventive actions based on the results of verification of management review for the continuous improvement of the system. And the results that we have, let us see that by saving the traffic records generated in the data network in great detail, facilitates their inspection for the analysis of subsequent contingencies in specific cases when we need to audit a connection. We used a dashboard and we deployed a dashboard on a web browser which facilitates the analysis of security, since it lets us visualize traffic statistics, analyze of cyber attacks carried out in a specific period of time, and it gives us a general overview of the traffic and security alerts generated. When we use the highest security mode, the system uses more computational resources, of course, and there is internal evaluation of connection of dubious origin, which are eliminated by excessive out-of-control traffic, which could be categorized as an attack. And the system stores the images which are transmitted through the data network and analyzes each one of them, extracting the text that they contain. For example, and this is an example that we have, as the system is analyzing an image and detects the text confidential, for example, actions are taken according to the rules that we previously established, and they can eliminate the connection, they can monitor the connection, or they can trigger other types of alerts in order to preserve confidentiality and anonymity. The system.
More. 2 minutes more.
Okay. When we have bar graphs, they are a useful tool because they help us analyze the traffic of the organization's employees. They allow inspection of activity in the internal network to detect performance problems or incidents. And when we have detailed bar graph with the number of a specific connection among the classified ones, we can observe the normal traffic, the lack of traffic control, the incidents classified as minor ones, new vulnerabilities to control, and new attacks that happen within the organization. And we have also an overview of the attacks that are carried out internally and externally. When a particular issue is observed while monitoring the traffic, any service access that does not have a secure connection implementation is going to be inspected. The results that we have show that security measures against incidents that occur on data networks usually are not noticed because security evasion techniques such as spoofing or RAG AP-based man-in-the-middle are increasingly sophisticated and require just a lower technical level. Even if the organization is attacked with new techniques that are not recognized by the security systems, when we have traffic stored, network traffic stores, we can analyze suspicious behavior and we can quarantine that until necessary. And as I mentioned, it's necessary to have metric on the attacks to measure the impact and keep the risk matrix updated. Early detection of attacks mitigates security breaches, and monitoring of networks really reduces the attack surface. We need to safeguard the pillars of computer security, and this experiment lets us see that it's possible. The implementation of security policies allows us to use a more detailed inspection of network events. And of course, traffic control is vital to obtain audit trails at any time. Thank you.
Thank you, Mr. presenter, Joan. I hope we have listened to his presentation and we have just 2 minutes to ask him questions. Questions? Any questions?
Yeah. So the presenters are, the other presenters are maybe busy by preparing their presentations. So Doctor, could you please share your input, question, or maybe feedback on the presentation and the idea from your side?
Did you hear the question very well?
Sorry, I told that maybe most of the other presenters are focusing on preparing their presentation. So
Okay.
unfortunately, we don't have any question pushed to the chat box. However, we would love to hear from you about your idea, feedback, or if there is any question from your side about the presentation.
Yeah, he has done very well.
Yeah.
It's only when he mentioned about the algorithm that they are using, and he said that the new detection scheme can only work if properly configured. I don't understand what he means by that. I don't know if he can explain further.
Yes, when we are using this system, we can choose to have high level of security, middle level of security, or lower level of security, and based on that, we are able to have the results that we receive. That's what I referred to when I said properly configured. We have a preference set up which allows us to go to high level of security, middle, or lower.
So the levels of security can be either high, middle, or lower.
Yes.
Okay.
Yes, and they work according to the necessity of detection that you have, the database of information that you have, if it has been recently updated, or also according to the amount of resources that you can use on your system based on connectivity, for example.
And the 3 levels can work together?
Basically, we choose the highest or the middle one, and they work independently, and they work one at a time.
Okay. Any other questions? Okay, thank you for your presentation. Because of time, we go to the next presenter.
Thank you very much.
Okay.
So yeah.
The next presenter, Fredis Simankan, study of data and internal propagation in electrical networks versus unshielded twisted pair.
Okay.
Can you make your presentations if you are there?
I think Mr.
Okay.
This is not here. The next one.
Okay.
Okay, so the next presentation will be for a paper titled Fully Passive and Assist Localization System Without Time Synchronization.
All right, let me share the screen first.
Yeah, please.
All right, I need to reconnect because of the permissions.
Okay.
Be back in a minute, all right?
We're sorry for such technical limitations, but again, we are doing a great job for being able to conduct all of our life activities almost normally by using the technology. So we are thankful for the technology, your support, and persistence. Our presenter is with us again. and we will listen to his presentation within seconds.
Okay.
Hi.
And this is ready. Here go.
Okay.
All right. Can you see my screen?
Yeah, we can
Yep.
see it. Go ahead, please.
Great. So let's start. So I'm going to talk about a fully passive unassisted localization system without time synchronization. So basically, this is the extension of TDOA, time difference of variable method. My name is Przemysław Świercz, and I'm an employee of Wrocław University of Science and Technology, Faculty of Electronics, Department of Computer Engineering. So let's start with background. So as of today, we have a growing number of mobile devices and mobile connections throughout the world. So right now, we have more than 3.5 billion people using the internet on their mobile devices, where the gap between people that are actually using the devices comparing to people that owns these devices, like it's half them, it's more than half during the past few years. So right now it's about like 10%, meaning that 90% of mobile devices owners do actually use their devices to access the internet. This also means that currently, as of today, 3.3 billion people live in the areas covered by mobile networks. All of that brings us to another numbers. So according to United States Census Bureau, the international database for population, right now we have 7.8 billion people on the earth, and the number is growing on average 1% per year. So on these graphs, we can see like the predicted number, the predicted world population in the next years. So even though the average annual growth rate is decreasing right now, it's still above zero. That this means that so comparing that to the other numbers, it means that more than half people on the planet, they own a mobile device. Yeah, and that's the number. So 3.8 billion, we have like 3.8 billion mobile users right now in 2021. Having those numbers like this gives the the importance of using actually mobile devices to locate people, to perform like a public service and public safety operations within metropolitan areas and within also urban areas. So there's a question why we should do wireless devices localization systems. So there's a lot of reasons. I've just marked 3 major reasons that are used worldwide. So first one is marketing, meaning that, for example, in shopping malls, in big area shops, if we could just localize mobile devices, so smartphones, mobile phones, stuff like that, this basically means that we are localizing people in these areas. So having that information, like where people are, where they're moving, where they're stopping, what they're looking at, like this is a very valuable marketing information that could be used to basically increase the income and to increase the industry of the marketing. The second area is the industry, heavy industry. So for example, the mining. So in the mines, it is very important to actually know how many miners do we have in different areas of the mine. So this is because of the safety reasons. Like for example, there are some regulations that in some areas there is a limit number of people that can be granted to access the area. So the proper localization system for this industry is extremely important because like this is people's lives depending on that. And the last part is public security. So in the context of COVID-19 pandemic, the government and governmental institutions, they need to actually control if people are keeping the distances or if people are gathering in a larger crowds. So of course, it's possible to actually use the GSM base stations to locate people, but it's not the case in most of the countries because of the legalization. So in most cases, you actually need to have a legal warrant from the court to access that kind of data. So this is why localization is extremely important nowadays. So let's go to the related work that we have right now. Localization systems can be broken down into two categories. So we have like self-localization system and infrastructure-based. Self-localization system is when the mobile device itself tries to localize, tries to get to know its location information within the area. One example of that is GPS, global positioning system. So like you have, for example, a smartphone with GPS module, meaning that your smartphone knows your position, and this position can be shared with other devices only with your consent. Just a note that GPS requires like 4 satellites, so the device needs to catch the signal from 4 satellites to actually to get the coordinates, even though we have like 3D-dimensional coordinates. Like we need 4 satellites because we need time synchronization. And there's also that note that GPS satellites, they carry anatomic clocks, meaning that they are perfectly time synchronized, because the time synchronization is the key here. If there are any time synchronization errors between the satellites, that would actually jeopardize the accuracy of the GPS system. So another self-localization system is eco-based, and eco-based means that the mobile device is sending a signal where the anchors, and by the way, what is the anchor? Anchor is a device with a known localization that's basically the part of the infrastructure. Anchor might be a GPS satellite, anchor might be a mobile base station, anchor might be a wireless router, Wi-Fi router. So how does it work is that a mobile device is sending a signal, an echo signal, and those anchors are receiving that signal and responding in a constant time, meaning that using time difference or partial methods, the device can actually calculate its own location. The third type of localization system for self-localization system is a visual localization. In most cases, this means SLAM, so simultaneous localization and mapping. An example of that is Google Project Tango. So how it works is that if you open your camera in your mobile device and you point the camera to some area, it's possible to calculate the location of the camera based on what the camera actually sees, based on visual remarks and visual information that is being transmitted from the camera. And there are many other localization systems that fall into the category of self-localization. On the other hand, we have the infrastructure-based localization systems. Infrastructure-based means that we actually need access to the infrastructure, but we do not necessarily need any access to the mobile device. This is why this infrastructure-based localization system can be divided into 2 categories. So assisted and unassisted. Assisted localization system is, for example, like reverse echo. So coming back to the example of echo, where the mobile device was sending an echo signal and the anchors were responding to that signal. This is the reverse situation where the anchors are transmitting the signal and the mobile device is responding. It's a small change, but it's actually it actually affects the way the system works, because in infrastructure based, it is the infrastructure that is localizing the device. So the device doesn't necessarily know its own location, but the infrastructure. So it could be a central node or central server. The infrastructure actually know the location of the server of the mobile device. An example of that is a GSM network. So if you carry your mobile device, your smartphone with you, this smartphone is in constant communication with a mobile device base station, actually with up to 7 base stations. So having information about the signal from your mobile device to those base stations, a mobile operator can actually calculate your location within their area, and actually the accuracy is quite high, quite high, especially in urban areas. So the study shows that it's possible to locate a smartphone in a city with the accuracy of single centimeters. On the other hand, we have unassisted infrastructure-based localization method. Unassisted means that the device doesn't need to cooperate with the localization system, and it doesn't even have to be aware that the system is deployed in the area. And this is what I'm going to focus on in the next slides.
Yeah, try to move fast for in the next 2-3 minutes to round off.
All right. So the whole idea is based on time difference of arrival, how it works. So if we have mobile device, this is the circle with number 1. So the mobile device is sending a signal. This signal is being received on three other anchors, so on 3 other stations. And if these stations have like perfectly synchronized clocks, so the time synchronized anchors, it's like relatively easy to calculate the position of the mobile device. So an example of that is Blizzardung. So Blizzardung is a service that actually shows you the location of the lightnings around the world, and this is based on TDOA method, because like the devices that are deployed around the world, they are basically synchronizing the time using the GPS. So this is time synchronized TDOA method. The related work about this is that there is one whistle system which, so we have 2 major differences between TDOA and related work. So one is that the device is actually required to cooperate with the system. So this is the reverse echo method. Number 2 is a whistle system. So whistle system doesn't require the device to actually cooperate with that. The difference is that in whistle system, the anchors also emit signals, meaning that the device can detect if it's in the area, if the area is being monitoring by the localization system. So the proposed method is to change the way we calculate the TDOA. So instead of using the absolute time for calculating the TDOA method, we measure the time between 2 subsequent or any 2 signals being received on the anchor. So this means that the method works when we have like more than 1 signal to be located, which in most cases is the case because every mobile device is sending a lot of signals every second, and that's also the case because the system is more accurate when we have more devices in the area, meaning metropolitan areas, shopping malls, and stuff like that. So how the method is defined. So what is being measured on the device is the difference of arrival, so the relative difference of arrival of 2 signals. So we have like 2 devices, 1 and 2, and we have 3 anchors, A, B, and C. Having that said, for 2-dimensional space, we require 5 anchors actually to be deployed, so from A to E. And this is because like there are basically 4 unknowns. So we have like 2 positions of signal sources. That's X1, Y1, X2, and Y2. And also what is unknown is the time difference, like the absolute time difference where those signals were emitted. meaning that there are 5 unknowns, and we need to solve this system of nonlinear equations. Having that solved gives you the exact position of 2 mobile devices at once. Also, what is a pro about this method is that it doesn't make any assumptions on the initial position of the signals. That's one thing. The other thing is that the anchors are completely passive, so they are not they're not sending any other signals. So the mobile device cannot detect that it's in the area that is being monitored. So let's move quickly to the experimental results. So I run the experiments on using acoustic signals. The reason is that for acoustic signals, the time, like measuring the time difference between 2 signals, is relatively simpler than for radio signals. So the accuracy for the system being deployed in the area of 10 by 10 meters is around 12 centimeters, and that, like, based on the assumptions and based on the experiments, the accuracy is not dependent on the number of transmitters in the area.
Try to round off because you have used your time.
Another result is that the system is stable in terms of like sequences of experiments. So the results are stable around 12 centimeters in the area. And there is one thing that really affects the accuracy, which is the smallest distance between anchors. So if we put 2 anchors too close to each other, the mean error is growing rapidly, meaning that we have a lot of error sources. So first, like, one of error sources is environmental noise. The other one is like multipath effect, but also mentioned geometry of the anchors. So that's the topic of further research. Also, like, if we have like time measurement problems, that also can affect the localization. Yeah. So final word: time different arrival methods are being developed right now. Based on this approach, we can develop a lot of methods. But what is important is that those methods, if you want those methods to be used as a surveillance method, we need to make sure that a system deployed in the area cannot be detected. All right.
Okay, thank you for the presentation, Mr. Precision. We have had your presentations, and then we give room for questions.
Yeah, so is there any question, any argument, or anything that need more clarification, our audience and presenters?
Can you come
Okay,
again?
Doctor. Okay, so it's complicated topic, to be honest, to have questions on, so we need time to process it. So thank you for thank you for the input, but I'm sure that our chair will have input question and supportive feedback to improve the work.
Thank you.
Yeah, I was going to ask him how he controlled the other environmental factors of noise, but he later was to talk about that. I know that when you are trying to measure a location, there may be other interferences. How do you factor those into the experiment?
All right, so during the experiments, I was trying to minimize the environmental effects on the system. And like, because I was using acoustic signals, I could do that pretty easily just by using like acoustic barriers around the area being monitored. But for wireless communication, for radio communications, we need to apply filters to signal receivers, meaning that with these filters we can minimize the multipath effect, and we can minimize the number of interference with other radio sources.
Okay, that's good. And it has not been fully implemented.
Yep.
You only tested with the experiment, not implemented yet.
that's implemented like I mentioned. So this is implemented with acoustic signals. Right
Okay.
now, it like the system with radio communications and radio waves. Like this is currently under works.
Okay. Thank you for your presentation.
Thank you.
We hope.
Yeah, thank you,
Let's
thank you.
take the next presenter.
Yeah, for sure. We will move now to our next presenter, who's also ready.
Okay.
Yeah.
Yes, hello, can you hear
Mr.
me?
Felix.
Yeah,
Yep.
Yes, you can hear me and you can see me, and I will try to share my screen.
yeah.
Okay.
You will
Yeah.
present a paper titled as redundant. I will back to the screen. Redundant bus system using dual mode radio. So yeah, we are listening. Please go
Okay,
ahead.
yeah, thank you very much for this introduction. Can you see my first slide?
No, could you please just share your screen again?
Yes.
Try to load again.
Yeah. Is this one? No, it should work.
Yep.
Yeah.
It's
Yeah.
there.
And maybe in presentation mode now.
Exactly.
Yep. It's fine.
Okay, thank you. So after these interesting talks about some higher level stuff like localization, I will come down to some more basic technology, let's say, talking about some basic technology like dual mode radio. So I'm now talking about some issues about embedded systems and mechatronic systems. And as you know, these kind of systems, for these kind of systems, communication is a key aspect. So exchanging data between small embedded devices or even bigger systems. And many of these systems consider a modern car with maybe some 100 small electronic control units. One key aspect for this communication is, of course, the real-time communication. So all the data have to be provided in real time to enable the functionality that should be realized. In addition, as more and more safety critical applications emerge, consider all this assistant driver function in modern cars, there's a need not only for the complete system, but also for the communication to be a safety. Yeah, that we have safe communication between all these nodes, like is shown here in this example for the FlexRay nodes. FlexRay is a bus system within vehicles that is dedicated, developed for safety critical communication. And as you can see, these FlexRay nodes between the ECUs, they use a redundant hardware structure. So how can you improve the safety features of communication and to ensure the data integrity during transmission is to add redundancy, both in hardware and in software. For FlexRay, as an example, it's really done in hardware. So you have two communication lines for safety critical communication. And you communicate the same data on both lines, and the receiver can compare the data and check whether the transmission was done successfully. Using these two communication lines, of course, has a big impact on the system with regard to, for example, the weight of the system, as you have to introduce all these cables and so on double. So what we tried to implement for this kind of safety critical application is another transmission medium. Is like radio. So we have a basic radio technology called dual mode radio, and we can use this dual mode radio for this redundant hardware path for the transmission of the data. These dual mode radios, so you can see on top here on the right side, it's a sketch of the transmitter, and on the bottom, it's a sketch of the receiver. And the basic idea of this dual mode radio is that you use a local oscillator. You split this oscillating signal into two paths, and both paths can be switched between two different new paths. So using now digital data 0 and 1, you can switch between two paths, both for the upper and the lower path. And you can introduce a phase shift between these two signal lines of either 0 degree, or you change it to plus and minus 90 degrees. So finally, on these two antennas, they are perpendicular oriented. You transmit two signals, and either the phase difference is 0 or 180 degrees. On the receiver part, you receive these two signals, you filter these, amplify, and you lead it to a mixer device. And according to the phase difference of 0 or 180 degrees, you receive 0 or 1. So using this kind of basic radio mode, we can transmit data in real time over the air without the use of any kind of protocol. So this is a real physical layer transmission mode only. Our current prototype we use is a discrete setup. As you can see here, the transmitter, and as well here on the right side, the receiver. So you can see the VCO, the two data paths for the oscillations. Here are the connectors for the antennas. Here again, the two antennas perpendicular oriented. And then here's the mixer, and then the generation of the digital output signals again. Our current setup uses a VCO with about 4.5 gigahertz, and we can achieve data rates for the signals with this very basic discrete setup of about 8 megabit per second, which is sufficient for example, for most of the bus systems used in automotive or industrial systems. The idea is now to enable a second data path for safety critical communication, not using cable again, TZ communication, but to use this radio link. And we made a very simple experimental setup for this parallel data transmission, taking the CAN interface, the CAN bus, which is a standard bus in automation systems and in automotive systems, and to show that the data on both the TZ communication way as well as on the radio link, they are the same both with regard to the received data and with the delay between the data. So we generate CAN signals, transmit these CAN signals via cable to the CAN transceiver here for the dual mode link, and on the other path to a second, on the 1 meter line, to a second CAN interface. We compare the data received on the TZ communication with the data received by the dual mode link and reconversion to the CAN data. And these data are then fed to the second channel of this CAN interface. And offline, we can compare the data received by channel 2 here and channel 1 here, so on the TZ and on the radio link. The analysis was done checking, of course, for the correctness of the data, and we compared the timestamps of the data afterwards offline.
Yeah.
Regarding data integrity, there were some erroneous messages received on the radio link where the CRC error occurred. So 2 and 1 of 18,000 messages were stuck with an CRC error. This can be attributed to our very simple discrete prototype setup. We have done other measurements of long time run measurements with an improved setup, and there was a very low bit error rate of something like 10 to the minus 9. Okay. At the highest data rate of 1 megabit, even no CRC error occurred, and all the data were received correctly, both on the TZ and on the radio link.
Okay.
And coming to the delay measurements, we measured the timestamps, compared the timestamps of both the data via cable and via the radio link. And as you can see, for 4 different data rates from 125 kilobits per second up to 1 megabit per second, the time delay between the received frames was very low, well below 10 microseconds.
Okay.
And if we calculate the average delay for the data rates, it's something like just 600 nanoseconds in time difference. And taking both the data integrity with some maybe misfunctions and the delay, we can conclude that this dual mode radio link adds just a very small latency to the data transmission, which is negligible regarding, for example, for the CAN communication. We have a robust and real-time capable radio link with this dual mode radio. So it enables redundant data transmission for safety critical applications, and that may improve data integrity for these kind of systems. Okay, thank you very much.
Thank you for the presentation, Mr. Felix. We give room to questions from the audience in case anyone has got a question.
Yes, please.
Okay. So yeah, our audience, is there any question? Because there is nothing pushed to the chat. There is an empathy from the audience because they don't want anyone to ask them, so they will not do it.
So for me,
Yeah.
was there no need for interferences?
So there, of course, there might be interferences for our setup. There were no interferences. And the good point about these dual mode radios is that we use two modes for transmission and these perpendicular antennas. So even if one of these signals is disturbed, that will not disturb our system setup.
As an embedded system, and it is considered critical, could you throw more light on why it's a critical system? It's a very obvious question, but I want you to throw more light there.
Imagine a modern car with some driving assistance systems, yeah, where the functionality is distributed on different electronic control units, and the data exchange between these units has to be safe. Yeah, that each system has the same data, and for these kind of systems, our dual mode radio might be a second link that the receiver can check for data integrity.
Okay. Can we say that that is the kind of thing that happens to the this plane that was having problems, sending error messages due to software failures and so on and so forth?
Yes.
Well, that's a good presentation. Yeah, it's in that line of reasoning. Okay. Thank you, Mr. Felix.
Yes, thank you very much, Mr. Ezekiel. Thank you.
Thank you, Mr. Felix. Thank you, our chair, for the contribution and input. And now let's go fast to the next presentation, which is about
Mr. Biswajit.
Yeah.
Performance study of ZigBee networks in an apartment-based indoor environment.
Yes, hello, I'm here. Yeah.
Okay.
So, can you please allow to share my screen?
Yes.
Yeah, just press on
We have seen your screen. Go ahead and share.
Okay. Yeah, got it.
Yeah.
So you can see my screen, right?
Yeah, we can see it. I hear you clearly. Go ahead, please.
Okay, thank you. So thank you. This is Biswajit Kumar Dash. I'm a graduate student of Intelligence Department at the University of Texas Rio Grande Valley. So I will present our paper, performance study of ZigBee networks in an apartment-based indoor environment. So in this talk, I will talk a little bit about our background and motivation. And then I will talk a little bit about the related works, our project's experimental setup, and how do we measure the data, the experiment and the result analysis. And then I will conclude the paper with a conclusion. All right. So the number of IoT devices is increasing day by day. So ZigBee is a very popular IoT technology that has been using to collaborate the different devices. with the internet. So a recent study shows that if 50 billion IoT devices will be added in 2030, by 2030. So there is a huge amount of devices, and due to a lot of devices, there will be a lot of collaboration between the devices, and there are other IoT networks except Zigbee. Like one of the popular is Wi-Fi, that we everybody has the Wi-Fi networks in our apartment or home. So Zigbee and Wi-Fi operates in the same 2.4 gigahertz ISM radio band, as you see from this figure. So they have a lot of overlapping channels to each other. Due to the wider band of Wi-Fi channel, a single Wi-Fi channel can interrupt multiple Zigbee channels. As you can see from this figure, Wi-Fi channel number 1 can interrupt Zigbee channels from 11 to 14. So there is a lot of difficulties to implement the coexistence of Zigbee and Wi-Fi when they stay at a proximity, and they operate in the same operating frequency. And most importantly, due to the lower transmission power of Zigbee than Wi-Fi, the communications of Zigbee suffer adversely than the Wi-Fi network. So this is the problem that we address in our paper. So in this paper, we analyze the purpose of a Zigbee networks in terms of with and without Wi-Fi traffic. So initially we do some experiments that there was no Wi-Fi traffic. So we measure the baseline performance of Zigbee network, and then we initiated a Wi-Fi network and the Wi-Fi traffic, and then we see how the interference from Wi-Fi traffic can interrupt the communication of Zigbee networks. So we use performance metrics like packet drop rate, receive signal value, RSSI, and the network throughput. And we use different communications parameters to measure the performance. That is operating channel, the distance between Zigbee and Wi-Fi devices, Zigbee transmission interval, and Zigbee transmit power. All right. So I do not want to put a lot of time on this area. So I'm to talk about like due to the popularity of Zigbee networks and Wi-Fi for IoT communications, the study between the coexistence of Wi-Fi and Zigbee has been a center point of attraction among researchers. So there are a lot of works has been done in this area. Like I mentioned a couple of them. In the paper, Dr. Abrigani talk about how the Wi-Fi networks can interference on Zigbee networks. So they use packet loss rate and average round trip time to analyze their performance. Also, there are works that has been done using overlapping and non-overlapping channel, the channel that are adjacent and alternate. And there are some real-time experiment has been done, like the experiment has been done in my reference 5. So they use different real-time environments, like how the wall, how the furniture in an apartment home can interrupt the signal of a Zigbee. And despite having some analysis, there are some solution has been provided in case by case, like in our reference 6, a solution called WiseBee has been introduced that can resolve the coexistence of Zigbee and Wi-Fi network in a particular case. All right. So in our paper, I talk about like our performance measure is based on 2 categories. So at first we consider a network setup that there is only Wi-Fi. Sorry, there is no only Zigbee network. So we have one XB module and one Wi-Fi that acts as transmitter, and one XB Zigbee module that works as a receiver. And in our another test bed, so we initiated a Wi-Fi network. So as you can see from this figure, so our focus is to measure the performance of Zigbee receiver, the performance of the Zigbee network in the receiver side. That means we are more interested to see how the Zigbee receiver act in case of interference that caused by Wi-Fi transmitter.
Okay.
So yeah, so first of all, we measure the performance of a Zigbee network without Wi-Fi traffic. So our aim is to get a modest Zigbee transmission interval that we can use for our further study. So we use transmission interval 100 milliseconds and 500 milliseconds, and we use the parameters like packet drop rate, and we vary the distance between the Zigbee transmitter, a Zigbee transmitter and Zigbee receiver to see how about the distance, how the packet drop rate can vary. So as you can see from this figure, 500 milliseconds obviously shows a greater or best result in terms of packet drop rate than 100 milliseconds. So we use this 500 milliseconds to measure the performance of Zigbee for our further experiments. All right, yeah. So in this case, we initiated the Wi-Fi traffic. So we consider three interference cases. So the first of all is overlapping channel. That in that case, as I mentioned this in figure 1. Yeah. So for example, in this one, the Wi-Fi channel 1 can tightly interrupt the Zigbee channel number 12. So we consider three cases. Sorry about that. Yeah, we consider three cases. So overlapping channel, and we consider another case adjacent channel. So that is not directly overlap to the channel of each other. And we consider cases where the channels are very far to each other. So there is no overlapping frequency. So in this case, we initiated 200 Zigbee packets from Zigbee receiver, Zigbee transmitter, Zigbee receiver, and in our setup, we use iPod software to generate Wi-Fi traffic. So our average bandwidth was 18.8 megabits per second, and we in the parameter level we change the distance between the Zigbee receiver to Wi-Fi transmitter. As I mentioned, we are focusing on the impact of Wi-Fi traffic on Zigbee receiver side. So as we can see from the figure, for the overlapping channel, the packet drop rate was initially high when the distance between the two devices, I mean Zigbee receiver and Zigbee Wi-Fi transmitter, was very close to each other. But over the time, the packet drop rate decreases. So the worst case has been found for overlapping channel. For the adjacent channel interference, as you can see, for a larger distance, the impact on Zigbee networks from the Wi-Fi traffic is getting minimal. So this is in real-time experiments. So we got the data from real-time experiments. So that these data comply with the theoretical analysis also. And for the non-overlapping channel cases, the interference from the Wi-Fi traffic on Zigbee side, there is no, we can say that there is nearly no interference. Though there are some packet loss or packet drop from the over the experience that can cause due to the less transmission time and interference, like interference from other Wi-Fi networks. Like we conduct the experiment in an apartment environment. So there are some issue like some interference might cause from a neighborhood Wi-Fi network. All right, then we use another parameter, a receive signal value, to measure the performance of Wi-Fi of Zigbee networks. So in that case, we consider when there is no Wi-Fi traffic. So for this experiment, our aim is to analyze how the Zigbee can perform with the distances. So in this case, we varied the distance between ZigBee transmitter and ZigBee receiver. So we consider 5 different values of transmit power from 8 to 8, 5, 1, -1, and -5. And we initiated 50 gigabit packet transmission from our transmitter to receiver. And as you can see from the figure, the best value or best performance has been achieved in case of the best transmit power. I mean the highest transmit power, 8 dBm. So this also comply with the theoretical analysis. So in that case, we can say like if we use more transmission power, then there will be better performance. But as IoT devices has very low computing power, so we need to maintain there is a trade-off between like how much we can initiate in the power level and how longer our devices can run. For the throughput measurements, we initiate Wi-Fi traffic. So in this case, we first measured the performance of the ZigBee network without Wi-Fi traffic. So we found this figure when there is no Wi-Fi traffic as a throughput. So we can say this is the best throughput for our network. And then we initiated the Wi-Fi traffic, and we found, sorry about that, we found as well as we found the similar incidence as it was for packet drop rate. For overlapping channel, the throughput was really low for for a smaller distance between the ZigBee and Wi-Fi devices. But over the time, the improvement we can notice the improvement, right? And for the adjacent channel, there was nearly no impacted for the longer distance. This is because when the distance between the two heterogeneous network can increase, then there is a less chance to interference to each other. And for the non-overlapping channel, as it was before for the packet delivery also, there is no noticeable interference to each other. So, all right, so I want to conclude like the ZigBee network performance decreased significantly, especially in the close proximity of another interference network. And the worst case has been found for overlapping channel case. There is no doubt that should be. So for adjacent channel, we can use adjacent channel if the distance between the two networks or two devices at a such distance that there is a minimal interference to each other. And if we use a non-overlapping channel, so the performance is optimal. That means it's near to the best value when there is no interference channel. So in summary, I want to say that the real-time ZigBee network deployment in apartment base, we need to focus the distance between the two heterogeneous network, as well as their channel selections. And in this work, actually, we somehow ignored the interference from other Wi-Fi networks in apartment. So to ignore the interference, we conduct the research or we conduct the project at the midnight when there was minimal or no Wi-Fi traffic from other neighborhood.
Your time is up.
Yeah.
Oh, okay, all right. So I am just finished. Okay, yeah. So our future will be to adding more analysis tools and a Bluetooth network in our experiment. Thank you.
Thank you.
Thank you for the
Mr.
presentation
Biswajit.
idea and the inputs. So is there any question from anyone of the audience? Any question?
Any questions?
We are almost at
Our
the end,
audience?
so no one will ask you back if you have already presented your presentation. So
Yes, I was going to ask him the difference between his figure 6 and a figure where he commented that there is that with the overlapping channel, over time you have got a decrease. Figure 6 and maybe figure 3 or 4.
Figure 4, yeah.
Okay, so what's the difference between that and figure 6?
Well, the difference is in this experiment we measured the how many packets has been dropped over the time and over the distances. So if the distance can increase between the two networks, in that case, the interestingly it's very opposite to throughput. So in the throughput, our performance, the network performance will be increasing because with the larger distance, the interference from each other, there is the less interference to each other for the larger distance. And the same thing here for the packet drop rate. So the interesting thing, like in the throughput depends on a different, not only the packet drop issue, but also the distance and the bandwidth of the interface network. So in the packet drop level, like we can say for a longer distance, there may be 5 packet drop, but in the throughput level, the throughput is not so bad as the packet drop, because the throughput doesn't depend on not only the packet drop, but also the depends on the other issue like bandwidth, the distance. So yeah.
Okay, although it looks obvious, but I was also going to ask you what's responsible for the decrease in overlapping channels over time. Because in figure 6, it looks as if it's just, yeah, if you can, I can't see it, but if you can move it. In figure 6, everything seems to be just, we don't observe the decrease there over time.
Yeah, so this is because like when the distance between the two heterogeneous network, like say the ZigBee receiver and Wi-Fi transmitter. So for the closer distance, the interface is very noticeable, right? Because the interface network can adversely impact our desired receiver of ZigBee. But when the distance increases, the interface like leads to be is getting less. So that's why the throughput is increasing over the time. But in the packet drop, like more packet drop is bad. So that's why our figure shows is decreasing. That means the performance is getting better.
Okay, good presentation. We go to the next one.
Yeah, please, let's go to the next one and let me get back to my screen.
Mr. GJ.
Good day. I'll be presenting in behalf of Mr. GJ.
Okay.
Yeah, sure.
Development and pilot testing of GoTrace, a web-based application for contact tracing using quick response codes. Okay,
Can
you have the floor.
Can you see my presentation?
Yes.
Okay. Good day to everyone who's listening. I am Rosaline Serene Julian from Cavite State University, Cavite, College of Arts and Trades Campus, Philippines. In behalf of my co-authors, Mr. GJ Bartolome, Ms. Mary Ann Ignaco, and Mr. John Patrick Buko, I'm excited to present to you our paper entitled Development and Pilot Testing of GoTrace, a web application for contact tracing using quick response codes. So let us begin with the reasons to contact trace. As we all know, contact tracing is considered by the World Health Organization as a principal public health intervention in containing the spread of COVID-19. Last year, the Department of Health in the Philippines suggested modern alternatives such as digital logbook applications for contact tracing. As policies and guidelines grow more lenient, establishments have been reopened to help raise the economy. As seen in the photos from a TV news report, the problem is that establishments use pen and paper setup that is high risk of spreading the virus, consumes time when encoding, and may be easily faked, damaged, or misplaced. The COVID-19 task force in the Philippines also endorsed applications for contact tracing. However, due to trust issues, the application failed to reach its audience. Because of this, other branches of the government and private sectors launched their own contact tracing methods. Our team compared the issues and features of these contact tracing applications. It includes A, end users are not comfortable of highly technical software if they do not know the particular data taken from them. Instead of using advanced technologies like global positioning systems and Bluetooth, the user should be the one to type, verify, and submit the data. The contact tracing apps that is used for a large scale, if not for the whole nation, tends to fail. The software should be designed for a specific environment and used for end user types. Letter C, compared to software that are forwarded straight to local government units, softwares that are implemented and controlled in an environment are maintained, monitored by a local system administrator tends to be more welcomed by the user. To come up with a solution, we use the agile software development model that enabled us to create design modifications even as the development continues. From unstructured interviews and focus group discussions with local health representatives and selected COVID-19 contact tracing participants, a unified health declaration form and computer-assisted contact tracing will overcome the challenges of inaccuracy of reports, physical delays, and it was also cross-referenced with existing health policies and data privacy considerations. From the analysis, the following outcomes were perceived. Two major components are identified, the front end and the back end. Faculty, staff, students, and guests are considered as the user types for the front end. Technical staff, healthcare staff, and human resource staff are the users for the back end. After identifying the system requirements, the software architecture was designed. The flow of contact tracing is as illustrated in Figure 2. First, the user must register and submit correct basic information. When the account is confirmed, the user can now use the digital health survey and contact tracing. On a daily basis, the health survey must be answered before entering the campus by selecting perceived symptoms and checking travel history. Then, a provided QR code posted on each office must be scanned to facilitate the contact tracing. Finally, the user will log out before leaving the campus premises. As summarized in the actual launching poster that we used, the health survey and the contact tracing is done in 3 easy steps. Register once, submit health monitoring survey daily, and scan QR codes. For the backend, the system will first ask if the user is registered. If the user is not yet registered, the system will provide registration link. If the user submitted a registered and verified account, the system will identify the user type. If the user type is a human resource staff, he or she will be able to access the login and logout records. Or if identified as a healthcare staff, he or she will be able to access the health survey and contact tracing records. Or if identified as a technical staff, he or she will be able to access the front-end accounts, tag locations, login and logout records, and the QR code generation. The software is developed using Bootstrap, CSS, and PHP, and JavaScript, meaning the app will run on all devices that has internet connection and web browser. As the development continues, a test case module was observed to identify, fix, and prepare for log defects and other bugs. This test case module will be discussed more later. After implementing the system, a survey questionnaire was used to solicit the feedback of 30 participants, consisting of 24 faculty members, a head nurse, 2 IT instructors, and 3 web developers. The results will follow the Likert scale, where 5 or excellent is the highest and 1 or poor is the lowest. Going back to the alpha testing, the table 3 shows that the test case modules, it considered 3 functionalities from the front end and 4 functionalities for the back end. Registration, submission of health survey information, and QR code scanning are included in the front end. While on the back end, 4 functionalities such as location adding, QR code generation, account registration, real-time viewing of health survey count, and report generation. All 7 functionalities passed the alpha testing before deployment. Let us take a look with the actual software that we developed. On the left is a recorded demonstration of the health survey submission in the front end. On the right side is a recorded demonstration of the dashboard reports records in the back end. Let me flash forward. I'll skip this one. Now for the end user evaluation, as described in the Likert scale before. For the end user evaluation of the developers, they gave the following ratings: excellent for functional suitability, excellent for performance efficiency, very good for usability, excellent for maintainability, and very good for portability. It has an overall mean of 4.46, interpreted as very good. The other end users gave an excellent rating for all indicators, such as usability, effectiveness, efficiency, satisfaction, context coverage, and this rated a 4.61 mean, interpreted as excellent. Now that we know that GoTrace satisfies its developers, end users, and experts, let us see the actual performance of the application compared to traditional contact tracing methods. In terms of contact tracing, the percentage of declared close contacts per participant is increased. The scope of contact tracing is scaled up by 40 to 30%, and the web application allowed prediction of COVID-19 hotspots and possible hotspots. For the survey forms, the percentage of retrieved daily health survey of participants is increased by 45%. It made identification of suspected COVID-19 case based on symptoms real time. It minimized number of forms to be filled out daily from 2 to 1 and shortened the average time in filling out a form from 30 to 60 seconds. Overall, the digital health survey and contact tracing allowed a faster data retrieval and an even real-time generation of various reports, promising results as based from the full adoption and implementation of the technology. The dynamic design of the web application supports customization for other environments. However, it is a must that the end user fully understands the significance and context of contact tracing as a strict measure to limit the spread of the contagious disease. The participants of the end user, the participation of the end user will significantly impact the extent of the scope of contact tracing and the quality of contact tracing information. And that's it. Thank you.
Thank you, Mr. Presenter, for the wonderful presentation. We give room to questions.
Yeah,
Okay.
the first question from if you please, just let me share the question from one of the participants.
There is a question from a participant.
Yeah, why did not you use Expo that allows the build of an Android and iOS application quickly?
Now, before that question, let me add,
yes.
Why is it that he considered it a web-based system instead of a mobile app? So you can join both. Why do you think it's best as just a web-based system instead of a mobile app?
Well, sir, because our users are consisted of students and other workers, which are considered in the lower economic status, and they have mobile phones which are limited in these specifications. So we choose to use a web base that will be used in all devices, even the lower specs.
Okay.
Did I answer your question, sir?
Yeah. It's linked to the question of the one of the participants asking you why you didn't make it an Android iOS app, which is easier and quicker to be implemented than the way you are doing it.
I guess I also answered that.
Yeah, but the fact is that you didn't consider the larger audience. You were just looking at your university environment or something like that.
Yes, sir. Yes, sir.
Yeah, but when you build a system that is going to be, that you hope to be used for the entirety of a nation, especially at this time of the pandemic, you don't just, this is just a test case. Let's say that this is your pilot study.
Yes, sir. We are actually developing.
Okay, it's a pilot paper, and so you hope to consider the larger audience of users in case it's accepted and implemented to be used in the Philippines. It will not just be for few number of participants. Okay, is there any other question?
Thank you.
Okay, so there is no other questions on the chat box. Also, there is a silence in the room.
The only other thing I wanted to emphasize, even though I didn't read the paper, is that he wasn't explicit on because when you develop a software as Go Trace, you will need your manual, complete manual. The flowcharts you were showing as design does not really show the design of the system. Those are flowcharts that actually explain what you are doing. If you needed to talk about requirements, like where you were talking about requirements, you needed to make clear statements on your functional requirements, what you expect the system to provide, and you state it clearly. It's not the flowchart you presented. So
Thank you,
in
sir.
in the paper, I hope you have taken care of that so that you don't present the flowcharts as the design.
Okay, sir. Understood, sir. We'll consider that. Thank you.
Okay.
Okay.
Yeah. Okay. Thank you.
So thank you for
Now,
the input. For sure, it was rich enough to extend the research and enhance the complete paper. Now, yes, doctor, we are moving to the next presentation.
Okay.
this is the next presentation. I don't know if it's going
The
to be
last
the
one.
last.
Yeah, it's the last
Okay.
one.
This is Mr. Janak. The
Yes,
shape
I'm going
nature
to,
of polar codes. Go ahead and present.
okay, I'm going to share. You need to allow me to share, please, the screen.
Yeah, you have the privilege to share the screen.
Okay. 1 second. Okay, for some insane reason, I'm only seeing whiteboard here.
Okay. If you need any help, just please share it with me on the chat, and I will share it from my side. No worries.
Yes, and you have the
You
permission
can
to
unmute.
share the screen. Yeah. I'm not able to share the entire screen.
Okay.
Yes, just a moment.
Can you leave it on the chat? Then they can share for you.
I'm sorry.
Attach it on the chat. Go to the chat, and then there should be a place for you to attach it, and then they can share for you.
Let me just try with the PowerPoint. I was trying to share a PDF, I guess. Let me try PowerPoint.
It's fine.
Yes, please try again. So just waiting for the 1 second now. We should be getting there.
If you go to the chat, you will see a place where you can actually attach it and then save it there, and then
okay. So I'm gonna attach the file inside here. Okay. Let me try and do that.
Okay. Okay. Send it to me directly.
Because it's not allowing me to share.
Yeah.
Strange. You would have thought that I would have access to. Okay, so I'm going to find the file. Just give me a second.
Oh, it's fine.
Okay.
I did not expect this delay, so I apologize.
The unexpected.
No, it can happen.
Okay, so here is the PDF coming across. And you should.
Yeah. Okay.
Yeah, it's there, right? It's right there.
Yeah.
So
I will.
Can you
share
try
now.
to?
Yeah. Sure, doctor.
You can share it, and then I'll just sort of let you know on the next slide. But I don't see anything as yet. If you could share it.
Second, please. I'm trying just to share.
She's trying to do that.
Yeah.
Normally, when we do Zoom, you're allowed to take over the entire screen, and so we can just show the entire complete screen. But for strangely, I don't seem to be able to do it.
It's fine, sir. Shit happens, but again, we are always ready to support. Yeah, here we go. And 1, 2, and 3. Here is the presentation.
Okay. So if you could put that in full screen, I guess somehow.
Yeah.
Put it in full screen.
Yeah.
Beautiful. Beautiful. I can see it. So that means you can see it. All right. So I'm looking at the shape and nature of polar codes. I lecture at the University of the West Indies, Department of Computer Science, Maths and Physics. Next slide, please. So error control coding, a very brief introduction. Block codes, 1920s, convolutional codes, 1950s. Then came iterative decoding in 1990, and then we realized that, hold on, we actually had we'd already discovered iterative decoding in the form of low density parity check codes, which was part of an MIT thesis in 1960. But the order in which error control coding has progressed is block codes, convolutional codes, turbo codes, low density parity check codes. And then came the magical invention by Prof. Arkin in 2008. And those polar codes are now within the 5G standard, the wireless 5G standard. On the screen, I wish I could take over the mouse, but I can't. So because you're sharing it, if you want to get into polar codes, on the right hand side, you can see I've put a note. Prof. Andrew from the IIT Madras NPTEL videos. If you take a look at that, that'll give you a wonderful insight into polar codes. If you wish to learn more. Okay, next slide, please. So what you're seeing there is a communication system model that I'm considering, beginning from the left to top left, and then coming around. So the source is a binary source, ones and zeros, which then get converted to QPSK signal points, and they enter a polar code encoder, which then enter your normal standard QPSK modulator, additive white Gaussian noise channel demodulator, and then a decoder and a sync. So my presentation is basically on the two blue blocks, the polar code and the decoder within this model of this communication system. Okay, next slide, please. Right, now this without the mouse pointer is going to be difficult, so you're going to have to stick with me. Right, so this is a binary tree representation if you're dealing with binary ones and zeros. If you can go down to the bottom where it says U1 and U2, yes. You know, U1 and U2 on this tree. So those two are combined.
The left side.
Yeah, on the left. I wish I had the mouse. I really wish. I don't know how I'm going to do this.
U1 and U2 on your left side.
There's no way I can take control over the mouse, can I? Okay, so I'm just
telling her she's trying to. At the base, where you have 0, 0, 0,
yeah, you got it right here where it says U1 at the very bottom where it says U1,
U2.
Yeah. I hear you.
Right, yes. You got me. Right. So U1 is a binary digit, U2 is a binary digit, and those two are then combined. If you look above it on that other node, which has the number 2 on it, there above it, you can see that U1 and U2 are combined, and whatever was U2 is then sent forward. So this entire mechanism of three different circles is a single node. And this tree represents the information bits M1, M2, M3, and M4, and they will traverse the system. And this is a very simple polar code, and you'll end up with 8 binary bits that have to be transmitted over. Now this I'm going to transform into a QPSK system. So if you could go to the next slide. Now, this might look like a nightmare, but it isn't. If you look at the bottom left, L11, L12, L13, L14, all the way to the end, these are the different levels of the polar decoder. And the manner in which the node is used are S and U. The manner in which they're used could happen through a complicated formula that you're seeing. That's based on log likelihood ratios. It's a lot of probability theory. But what I'm trying to show in this paper is that we really can view this entire polar code decoder very simply as nothing more than shapes that move through a tree. If I had a pointer, I would get into all the maths, but I don't. If you could go to the next slide, I think I'll make this very simple. Keep going to the next. That's it. Next slide. Yeah, that's it. If you just maximize the screen.
Yeah, it's full screen.
That's it. That's perfect. If you can maximize it. Oop.
Sorry, it's a full screen.
Yeah, it's a bit difficult.
They thought
there we
go. Go down. Yeah.
That's it. That's it. All right. So if you look at a given node, R, S, and U, and you look at the table on the right-hand side, and you were to look at the QPSK signal points, then you would, and if you look at the diagram with a circle, green grid, and a circle, you can see that if you were to look at, let's take, for example, where it says horizontal line in the table, 0, 1. If you were to draw a line between 0 and 1, that's a horizontal line.
Yeah.
1 and 0 is a horizontal line going the other way. 2 and 3 is a horizontal line, 3 and 2. So
Yeah.
if you were to encode in this way, life becomes very interesting and very simple. You basically have a combination of vertical lines, a diagonal line, and a point. So the manner in which I'm going to use S, U, and R is I'm going to take R, connect it with U to create either a point, a horizontal line shape, a vertical line, or a diagonal line. And that is what's going to go through the system. Okay, if you could show me the next slide, the next page. So again, this is going to be difficult without a mouse, but basically the function F demodulates, it's in the bottom right-hand corner in an orange box. The function F basically demodulates the incoming signal points R and U. It then uses the table, or it uses XOR operator to find the symbol S and assigns it the XY coordinate values. And the function G is on the right-hand side, and it just basically utilizes the coordinates of U and R in order to estimate U, depending on if S is either 0, 1, 2, or 3. I apologize, if I had my mouse, I could really get into it, but let's go to the next slide. The point being is that I can very quickly take log likelihood ratios and bring them down to shapes. This is the entire algorithm. So if we start at the very top, L1 on the top green, L11, L12, L13, all of those in that green box are used to determine the green box level below. So L21, L22, L23, and then those 4 are used to determine L31 and 32, and 31 and 32 are then used to determine 41. So it works its way down like this. The algorithm is there for you to see. I was going to go through it step by step by step, but it works. The key point is that it works really well. So if we go to the next slide, that shows the simulation results. And the blue curve is what would happen if you used uncoded quadrature phase shift keying. And the red curve shows an improved probability of an error. The red curve is good. We've got a coding gain of about 2 dBs. And that red curve, if it was more and more towards, if the slope was even more, then that's a better error control code. And of course, we can improve it as we wish. The point of my paper is to show that even with a very simple polar code, instead of using log likelihood ratios, you can bring it down to shapes that traverse the tree, and the decoder utilizes it. Okay, into conclusions. So basically, the paper has shown that polar encoding and decoding was extended from binary to process quadrature phase shift keying symbols. And it's, of course, it's valid for any size of constellation MPSK. A given node, within a given node of the three nodes, it can be seen, S can now be seen as a controller, and the transmitted shape is the symbol R connected with symbol U to form either a point, a horizontal line, a vertical, or a diagonal line. And this opens up research into the use of more complex shapes and to increase the code rate. It is possible to increase the code rate easily. So the aim of ongoing research is to create a shape, not necessarily based on the modular 2 operator, which is what I used throughout the thing, but a shape that spans several nodes. If you look at the right-hand side, at the bottom right-hand side, right now the shape is limited to 3 of those, U1, U2, and what's above it. But you could envisage a system where a virtual shape is embedded throughout the tree, much larger, much complex, and then that would traverse through. In a real 5G network, instead of having U1 to U8, that would be U1 to 1024. That would be a typical 5G frame. Okay, I believe that's 12 minutes. Thank you very much. I'll put on my video, at least. Let me see if that works.
Yeah,
Okay.
I would like.
That works, great.
Yeah.
That works, wonderful. At least something worked.
Yeah.
Okay.
Well, thank you for this wonderful presentation. You have displayed your discipline. Do we have any questions?
No, I don't think that anyone will be the brave to ask any question.
Okay,
Doctor.
okay. Now, I just have
You,
to.
Doctor, for sure have your input.
Here is a nice presentation. Is it part of coding theory or information theory?
Yes, it's all information theory. It's all coding theory. Exactly. Exactly.
So what happens if the binary tree has got several children? Do you consider the impact of the NOC, the number of children, if a binary tree has got too many levels?
It does increase complexity, and it does slow down the system, but there are many efficient algorithms to deal with a tree. So it really was an impact, but it's no longer an impact. That's not an issue right now.
You didn't check it, or you are sure it doesn't have an impact?
It does have an impact, but it's not of real consequence given the very efficient manner in which a tree like that could be attacked. It need not be the manner in which you saw me start from the top, work my way down to the bottom, and then go up and down and across. There are many ways to sort of really zoom right into it. So from what I've seen, the impact on the throughput and decoding speed and complexity, it's not an issue right now. The main point of the paper is to show that, look, we really could view this entire decoding algorithm from the form of shapes that traverse the tree that can be used to improve error control coding. Thank you for the question.
That's a nice presentation. And we thank you all participants for attending this session. It's been wonderful, and the presentations are very good papers, and we hope that we have learned good things out of this session. And in the absence of no questions or no other comments, I think we can just close the session right here.
But if you please, can I have just seconds to have my own closure?
Okay.
So my closure will be by thanking you for the great way of managing the session, answering the inquiries in a smart way, and asking questions that added a very indeed contribution to the audience in their presentations. It was great and different from other sessions, so thank you for your contribution. It's a simple appreciation certificate for you, Doctor, and for our audience and the presenters. Thank you for your time. Thank you for being part of this conference, for the great contribution and presentation. They were all informative and knowledgeable. Regarding the certificates, you will receive it within a couple of business days, so please make sure to check your inbox within the beginning of next week. For the publication, don't worry, we have already pushed the needed information to Springer. They will be there within 4 to 6 months. It's worth to be patient, but for sure you can follow up with the support team at any time. So thank you for being part of this day and this session. And even it's virtual, we will have a chance to have a picture together. If you don't mind, open your cameras. Let's make our memory, and hopefully next year we will see each other physically and have it by the classical camera. We will not ask for anything digital after the digital transformation. Okay, dears. So thank you again, and I will take the picture after counting to 3, 2, 1.
Okay. That's
so
nice.
So thank you, and I appreciate everything that you have presented today. See you soon. Please stay safe and take care. Bye-bye. The next session will start within less than 1 hour. See you there.
Okay. Thank you. Yeah.
Okay, bye-bye. Bye-bye.
Okay.
Yes, thank you, everyone. Thank you, Feroz, for moderating the session. Thank you.
Thank you, Dr.
Thank
and the
you,
audience.
Feroz.
Bye-bye.
Thank you, Aki.
Yeah. Thank you. Yeah.